we'll start here. So begin the iteration. Say, if you say A is accumulator, B is the divisor, and Q is the dividend. So what is that we do is, first try to take all zeros depending on what you say, the size of the magnitude or the size of the value, what you are considering as the dividend or divisor. And the B value, your divisor is stored, and this Q is dividend. Okay. And make the count equal to n. N is equal to the number of bits in your A and B sort of thing. Now, first, after taking A and Q, directly take left shift. Both your A and Q put together. Now, here try to see what is the value of like A. Is it less than 0 or not? That means for this, we try to take A of n bit. Okay. So if it is false, less than 0 false means positive number. If this is true, means that it is negative number. If it is negative number, try to add the divisor to A value and store it back in accumulator. If it is positive value, something like we need to subtract the divisor from A, or else it is equal to add 2's complement of B. Okay. After doing this iteration, again check back what is the value of A, whether it is greater than or less than 0. So if A is less than 0, that means we are checking for whether it is positive number or negative number. Okay. So again, false and true. Based on this value, we try to fix the value of Q naught, which in your earlier restoring division also we have taken the value of Q naught. Deciding the Q naught value depends on whether the A value is positive or negative. So if A is positive, that means the value stored in A is positive, then take that Q naught to be 1. If it is negative, take Q naught to be 0. Okay. Then decrement the counter. Sorry. First decrement the count, then check what is the count value. Count is count -1. Then check whether count is 0 or not. Once you decrement, if the count is 0, if it is not 0, you repeat this iteration until you complete the what you say n number of iterations. If your count is complete, that means the n number of iterations are over. I think this is equal. It is equal to 0. If this is false, do the iteration. If it is true, again you check what is the value stored in A. That means almost 3 times we will be checking whether the value stored in A is positive. Someone is speaking. Ritvik, any doubt? If this is true, that means negative number. If this is negative value stored, then what you have to do is final iteration of adding the divisor into the accumulator. If it is false, that means positive. You need to begin means end. Okay. This is the final thing. So restoring and non-restoring, what is the difference we are having is, in the step of restoring, we were adding back or retaining back the value of A once the iteration of the shift is over. Okay, once the value of your Q0 is decided. But here non-restoring thing is, we try to take or assess the value, what is that available or stored in accumulator, whether it is positive or negative. Based on that, what to be done, what iteration has to be performed onto A value, whether it is subtracting or adding the divisor is decided. Then what is the value of Q0 that you have to consider will be decided again. And the final thing is that after completion of total number of operations, that means n number of operations, final check we do is whether the value stored is positive or negative, or the value what you're obtaining after n iterations is positive or negative. That decides whether to take the result as it is or add the divisor and take the result. Okay, maybe one example if I can take, you'll be able to understand. Okay, so let me take the divisor value, say something like 5. 5 is plus 5, 0, 1, 0, 1, minus 5, this is B. Okay. B dash, that is equal to 1. Let me take the sign bit also. 4 bit I take along with the sign bit if I take. Okay. Extra bit I'm taking. 1, 1, 0, 1, 1. Complete. And say dividend. Let me take as 7. It's positive 11. 1, 2, 4, 8, 1, 0, 1, 7. Okay. Okay, we'll start with A and Q. Okay, sign bit and the magnitude bit. Sign bit and the magnitude bits. And Q is normal magnitude only. That is 1, 0, 1, 1. Now, what is the first step we have to do? This is left shift. Direct left shift we have to do. Left shift means this way. This way. So 0, 0, 0, 0, 1, 0, 1, 1. Now this vacancy will be decided. The value of this Q0 will be decided based on the value of your this sign bit. This sign bit is now here what we take is a of n, I said. So this is a of 5. If you start with 0, this is 4. If you start with 1, this is 5. Okay. So MSB bit of A will be taken. Now 0 indicates what? Is it positive or negative?
Positive.
Positive.
Positive. Positive means we need to do a subtraction. That means adding the 2's complement of B. So the 2's complement is 11011. So this is 0, 1, 1, 1. Now again we need to check whether this A value is positive or negative. So the sign bit is 1 indicates that it is negative. If it is negative, your Q0 bit will be 0. So this bit will be 0. So 1, 1, 0, 0, 0, 1, 1, 1. This is after fixing the value of Q0. Now what we have to do, we need to do the decrement of the count. See, decrement of the count. Then it is not complete, so back we go and do a left shift. Left shift 1, 1, 0, 0, 0, 1, 1, 0. Now this Q0 has to be decided. Now this is less than 1 or less than 0. Sorry, negative. Negative means we need to add. We need to add B. So what is B? 0, 0, 1, 0. Add B. Now 1, 0, 1, 1, 1. And this sign bit of A indicates that it is negative. Then Q0 bit should be 0. This is 1, this will be 0. If this is 0, this is 1. That is a blind way we can take 1, 1, 1. Okay. So after this, what we do, we decrement this. We decrement the count and do the left shift once again. When you do the left shift, 1, 1, 0, 1, 1, 1, 0, 0. So doing the left shift. Now, see here. Again, A is negative. Negative means we need to, again, negative means we need to add the true value. That is, true value is 0, 0, 1, 0, 1. The one what you get here will be discarded. And what is that remaining is your A is 0. That means a sign bit of A is 0, indicates that it is positive. So your Q0 will be 1. Q0 will be 1. This will be made as 1. And this is the remaining. So how many iterations are over? One more we need to do.
3, ma'am.
One more iteration we need to do. So do the left shift once again. 0, 0, 0, 0, 1, 0, 0, 1. This is positive. A bit value is positive. So when it is positive, what is that we need to do? A plus B or No. Positive means minus, na. Minus. Here, positive means it should be minus. I'm not taking the final thing. Still one more iteration is needed, not this step. This step we are at. So add 110, 112, and this will be your A value is negative. So Q naught will be 1, sorry, 0, 1, 0, 0. And this is here 1100. And see here, totally, we are doing the division of 11 by 5. What should be the result for us? Okay. And we are at this place now. We completed the total, what you say, the division process, and the final division, or what you say, the result consideration is based on the value of A, or the sign bit of A. If it is less than 0, we need to add B. We need to add B in order to get back the original value of the result. Okay, so something like 2 and the remainder will be 1. So here what we have to do is add this B back, so that the result will be, and this we discard, and see, this is the portion of, this will be your, what you say, this is the quotient. Q gives you the quotient, and this gives you the remainder. So what is the remainder? 1. What is the quotient? 2. So you are getting this. Okay. So until this, it is nth cycle. We completed n cycles here. Completing n cycles, final check of consideration of result is based on the value of the sign bit of A. Okay. If it is directly something like positive or negative, we try to take based on the value of sign bit. Okay. If it is false, indicates that it is positive number, directly the result will be A. If it is negative number, then we need to add back the value of the divisor. So this is your, what you say, the restoring and non-restoring aspect. Two aspects we have seen, restoring and non-restoring division. Okay, so this is something what we have in the syllabus for the division for you. You try with another values leisurely, something like say 23 by 4 is there, sir. Do with this, or 13 by 8, do with this. Try to evaluate these two as the assignment question. Restoring division for 23 by 4 and 13 by 8. Okay. Another sort of multiplier I'll take, array multiplication. See, I'll be switching between adder, multiplier, divider, subtractor sort of thing, just to follow the content only. Okay. So normally when we are doing a multiplication process, say if we are doing n bit multiplied with n bit value, how many iterations are needed in total? How many iterations are needed in total? Something like n partial products are needed. Okay, n partial products are needed, and how many full adders are needed for it? How many full adders are needed? n into n full adders are needed. If you can check it out, something like say 4-bit into 4-bit if you are taking um, something like this, say P1, P2, P3, P4 into M1, M2, M3 and M4 you are taking. 4 partial products will be coming. Yes, each of 4-bit size. And when you are performing the operation, we are adding this stage, this stage, this stage, and you'll be adding that. And the operations what performed are the full additions, no? Along with the carry coming from the earlier stages, you will be adding the partial product value to define what is the ultimate sum or what you say ultimate result. Okay, so for this, the number of iterations becomes something like a product of the bits, how many you are taking. So this is something like we can say it as a spatial operation we are performing. Spatial operation we are performing, and here in your say a binary format of multiplier we are taking, say when you are deriving the partial product, can you say that there is some commonness or common element that is repeating there? A common element that is repeating in your partial product.
Yes, ma'am.
Is there any common element that is repeating in your partial product? See, based on the bits of your M, whether it is 0 or 1, whether it is 0 or 1, if it is 0, what will be the partial product? A multiplier is 0. What will be the partial product? All zeros, no? Multiplier is 0, the partial product will be 0. Like if the multiplier is 0, if the multiplier is 1, then it will be the P1, P2, P3, P4 as the partial product. That means this is the one what is getting repeated, no? Like 0 anyhow, it depends on whether your multiplier is 0 or 1. We are defining whether the partial product is 0 or the what you say the multiplicand itself getting repeated. So the parameter of multiplicand is the repeating factor there. It gets repeated. Okay, and when you are, this is your partial product element I am speaking of now. This is partial product. Now when you are taking the full addition operation, what and what will be getting added? We are using a full adder for getting this result. We are using full adders for getting these results. What and what needs to be added is the partial product of that in place thing along with the previous element, that means previous value of the addition. You are adding the previous carry that is getting generated because of the addition of the previous stage partial product. Okay, so this is something like we can take this type of addition as the array format, and we what is the operation that is performed is multiplication. So maybe if I can put this into a little bit elaborate thing, I said this element is the one which is getting repeated. So if I take an AND operation, okay, which is having P1, P2, P3, P4 as the independent inputs of the AND gate and one common element of the multiplier bit. Am I able to get the partial product now?
Yes, ma'am.
For getting either all zeros or the partial product, I said if the multiplier bit is 0, this all elements will be 0. If the multiplier bit is 1, then this will be P1, P2, P3 and P4. That means now this segment, I'm able to generate the partial product. Okay, if I repeat this setup, for what you say, m number of times, how many bits I have in this m, then I'll be generating the partial products of the total iteration. Yes, and later portion is that uh, doing a full addition. First is generating the partial product, then doing the addition. So something like this. I can put this as, say, 4-bit element if I take. Okay, say P1, P2, P3, P4. This becomes, say, start with this side and 4. Next. Next, what is the element we need to shift? The same 4 AND gate setup. And again, here also this will be the partial product P1, P2, P3, P4, along with the multiplier M3. So that happens, this repetition we need to do for 2 more steps. Now this will be M2 and this will be for M1, the control element. Okay, later we'll be doing the addition process. Now, in between, to complete the total multiplication process, what we need to do is, we need to take, say, between these 2 steps if we are taking, we need to have a full adder. Yes or no? Yeah, 1 second. 1 second, I'll be coming back. Dheeraj, Varun, or Varun? Only 100 students are there? 98 only? The others are in class or what? Any other student can respond if Varun speaker is not working.
Ma'am? Hello?
What happened? Only 100.
Hello, ma'am?
Only I'm able to see 98 students there.
Hello, ma'am?
I'm able to see only 98 students. What happened? Am I audible? Is my voice? Varun is not audible for me. Anyone respond? Is
Ma'am,
my
you are
voice
audible.
clear? Audible?
Yes, ma'am, you are
Yes,
audible.
ma'am, you are audible.
Yes, ma'am, you are audible.
Why so much less attendance? "98 students" means it's only half the class, almost 60% only is attending. 40% what happened? Okay, let it be. It's not my duty to check your attendance. I'll complete my syllabus, that's all. Okay, so in between your iteration of generating the total result of the multiplication is that generate the partial product, do the full addition on all the partial products, and each stage in between needs complete full adders. In between two stages or in between two partial products, we need one set of full adder, complete one set of full adder. So this is something like spatial operation we are saying, and this needs how many sort of inputs and outputs is that if I can take one segment, say if I take one segment, any one segment, if I mention if this is one segment, what are the things that will be generated? See, from the AND gate, okay, having the P parameter P of I and the M of I multiplier bit. Okay, what is that we get is one of the input to the full adder we will be giving. One of the what you say, the full adder input will be derived by this element of AND gate, because in between every stage we have a full adder we are saying now. So here this full adder will be giving you the carry as well as the sum. Full adder will give you the carry and the sum. And what is the next input that will be given is the addition output, or the after performing this operation of generating the partial product, the previous stage partial product will be coming as one of the input to the full adder. Okay, got this now. The iteration will be generating a sum and carry. This becomes the input to the next stage. Say if I have one more say P of I, say this is M of I plus 1 if I take, this becomes the full adder, but this becomes the, so this is the partial sum product. You can say the sum of the partial product from the previous stage, and this gives you the carry, and this gives you the sum. So this segment we can have a C of in. Where from the C in comes? Where from the C in comes? The C in will be the C out of the next, say, one more full adder if you have. This C out will be C in here. This will be C out. This will be sum. And this is your partial product with the multiplier, the in place bit, the multiplier bit, and the previous partial product. So hope you understood what is this segment. So this segment, if you repeat, this is the what you say, one bit or one bit adder partial product element. This we repeat for n number of times, n into n, because this is array multiplication. You'll be able to perform the n into n multiplication process. This is your array multiplier. I'm not giving any example for this. This is self-explanatory only. The thing is, how many number of bits you are taking, how many segments you need to repeat, you have to see. Say something like 4-bit itself, if you take, let me give the diagram format so that you will be able to understand the operation of this array bits, array multiplication. So this is, say, P3. What is the order I took? See there, whether it is P2, P3, P1 format. Or you can take this as P1, P2, P3, P4, whatever the format. Say if P0, P1, P2, P3, I'm multiplying with M3, M2, M1, M0. Okay, for this I'm drawing now. Now first one will be, sorry. This is M0. Okay. And this fellow gives us one of the input to the full adder. This full adder okay. Now we need to get this is the first stage, means C in will be 0. Okay, and this will be C out and this will be C in. This is C out for this block, and the same way this is C out, C in. I'm taking CO and CI sort of C out, C in, and this will be C out. Okay, and see here. Now for the next iteration, the sum generated from this first stage will be taken. Okay, and one bit shifted, we need to take the partial product. Okay, and now this becomes P3, P3, P2, P1, P0. Okay, and this will be M1. Okay, now see here, this try to make the difference with the colors only. It's not so clear in drawing. And now this is the carry out, carry in, carry out, carry in, carry out, carry in. And this is again Cin, which is 0. And this repeats. How many stages you have? That many stages you will be repeating this. So this element is the repeating element for us. So this segment is the repeating segment. If you repeat this for n into n number of times, or n into p, say if m into p sort of thing, m into p number of times, you will be getting the array multiplier output. This takes much of the hardware, if you can see. This sort of multiplication is simple, or the earlier Booth's multiplication is simple. We have seen one more multiplier, no? Modified Booth's multiplier we have seen, and normal Booth's multiplier we have seen, and this is array multiplier. Which one is simple in terms of hardware, if you can visualize? Which one is simpler?
Modified one, ma'am.
Recorded Booth's multiplier is more simple when compared with the Booth's multiplier or the array multiplier. The number of gates are huge here in this array multiplication. That's why we are taking that paired sort of bits, paired bits we have seen there in the recorded Booth's multiplier. Okay, so this is something related to one type of multiplication, or the format of multiplying, taking the complete partial products and the full addition methodology. Another multiplier what we have is a sequential multiplier. And this sequential multiplier is a little bit simple sort of thing, we can say, wherein we try to use the concept of right shift and add. Right shift and add, and this adding process is it depends on a condition. Right shift is common. Right shift with add or without adding, we try to do the multiplication process. For this, what is the iteration, or what is the procedure is, we try to take the same accumulator and the quotient, the multiplier sort of thing into the AQ registers. Okay, and along with we have one element of what we say a carry element also taken towards the MSB side, and the complete CAQ bits will be the result bits. The complete element of C, 1 bit, n bit of A, n bit of Q. 2n plus 1 bits will be the total result will be considered. So for this, maybe how we perform is that always we try to see the value of Q0 here, the Q0 bit, in such a way that if this Q0 bit is 1, we just try to do the right shift. If this Q0 bit is 0, before right shifting, we try to add the the multiplicand bit. Say I take M is the multiplicand, then Q is multiplier if you consider. So into the accumulator, we add the multiplicand bit and then store. If Q0 bit is 0, okay, then we do the right shift. Then right shift. If Q0 bit is 1, direct right shift. if Q0 bit is 0, we will be adding the multiplicand bit to accumulator value. That means here, A plus M means here. Then we do the right shift. Again, we check for Q0. Again, either do the right shift or add the multiplicand, do the right shift. These are the two iterations what will be completing the multiplication process here. Okay, so let us put it in a simple flowchart form so that we can refer that back. So beginning, you try to take CI bit and A is fed with all zeros. How many bits you have? Many zeros. And make the Q as the multiplier and M is the multiplicand. Okay, then after you fill the values, check what is the value of Q0. If it is 1, if it is true, or if it is 0, false. If 1 is 0 is false means it is 0. Then if it is 0, directly do the right shift. Right shift. And doing so, you do the count decrement. Okay. And if it is 1, Q0 is 1, if it is true, then what you have to do is you try to take the multiplicand added to the accumulator, then do the right shift. These are the only iterations we are performing. And after decrementing the count, see whether the count is 0 or not. If it is not 0, try to do the check for Q0 value once again. If it is true, complete, the count is 0, then stop. Start means stop. That's it. So this is the simplest um, multiplication procedure. Okay, let us take one. Seven into 5. So what is the result? Should be 35. So I'm taking M is 7, that is 111, and Q is 510. We don't need this 2's complement or 1's complement because there is no subtraction. It is only the addition of the multiplicand alone. So we don't need to have this 1's complement of any of the value. Okay, so these are unsigned numbers we are taking. If you are doing this for signed numbers, we need to have the sign bit and do the sign bit extension. If negative numbers are there, okay, do sign bit shift or sign extension. Sign bit extension shift has to be done. For positive, direct shifting. Okay, so sign extensions are needed while handling the negative numbers. For positive numbers, there is no need. Okay, let us take this C A Q. C is 0, A is initial 0 0, Q is 101. This one 101. Now, what is the value of Q0? This is Q0. Q0, Q1, Q2. So Q0 is 1. Q0 is 1. What should be done? We need to add the multiplicand and see what is the result. Okay, so 0, 1, 0, 1. We need to do the right shift. A plus M, Q0 is 1. So these are the iterations needed. Right shift means it should be, this should be coming here, this will be coming here, and this is 1, 1, 1, 0, and this is 0. Now the difference what you have in your sign with negative values is that this sign will be extended. One more sign bit will be taken, and that sign bit will be extended. If this is 0, it will be 0. If this is 1, it will be 1. Okay, extension of sign bit. I think that sign bit extension we have seen in the previous examples. Okay, now here after this first iteration, now you decrement the count. Now check the value of Q naught. Q naught is 0. Q naught is 0. What is that to be done? Just to do the right shift. Because Q naught is 0, do the right shift. 1, 1, 1, 1, 0, 0, 0. Okay. Then here Q naught is 1. We have decremented one more time. So next iteration is Q naught is 1. 1 means here it should be accumulator value should be getting added with the M. So this is 0, 0, 0, 1. And this is 1, 1, 1. So now you do the right shift. Doing the right shift, 1, 1, 0, 0, 0, 1, 0. Because this is both positive numbers, we are not taking the sign extensions, directly shifting you are doing. Now you decrement the count. Now that completes 3 iterations. 3 bits were there, 3 iterations over. 1, 2, 3 iterations are over. Now here this is the value of the result that you have to consider all the bits together. It's not like a division of CAQ sort of thing. CAQ all put together will be the result. That means this is 0, 1, 0, 0, 0, 1, 1. So this is 1, 2, 4, 8, 16, 32. So this should be equal to 35. So this is the result. Your sequential multiplier is very simple. Simplest to form. Okay. You can have your own examples or the values you consider. Then you try to do on this. Okay. Any doubts here? So I'll take 5 minutes break and I'll take up the next topic. Okay. 5 minutes break we'll have.
Okay, ma'am.
This is not sign extension thing. Both are positive, na? Only for negative, we need to take the sign extension. I said, if negative numbers, do the sign extension shift. Sign extension shift. Positive, it is directly 0. here. Next, prefix adder. Heard of this adder? Or parallel prefix adders, we'll say. Carry look ahead adders or your ripple carry adders. Carry look ahead, you remember? Carry look ahead adder.
Yes, ma'am.
Something like we are taking or we are looking ahead of the value of the carry at that present stage based on what you say the previous bit values along with the present bit values. That is your carry look ahead addition. Something like we can put this into like this addition process. Say parallelly, I'll be taking this concept linked with this concept. Try to link these two together so that it will be easy for us to understand this. So in the carry look ahead addition, something like say if in place bits A and B what you are adding, if you are taking this as AI BI and this is the carry coming from the previous stage, what is the state carry coming here in that ith condition or ith stage? Something we can visualize this into a condition of either a carry kill condition or a carry generate condition or a carry propagate condition. These are the what you say the probable outcomes of the addition of the in place bits with the previous stage carry. So something like if the in place bits are 0 0 0 0 with previous stage carry 0 or 1, in place bits 0 1 with previous carry 0 or 1, 1 0 previous 0 or 1, 1 1 previous 0 1 1 1. That's something we can visualize this as if you have the two in place bits as zeros, okay, you have the condition of the carry that is being generated or that is coming from the previous stage will be killed. There won't be any carry, whether the in place bits like whether there is a carry from the previous stage or not. If the in place bits are 0, any value of the carry coming from the previous stage or there is no carry, the meaning of this too, the carry of that stage will be 0. So this we call it as kill condition. This is carry kill condition. And when in place bits are 1 1, in place bits are 1 1, okay, whether there is a carry from the previous stage or there is no carry from the previous stage, these two conditions, obviously there will be a carry generated. So this is generate condition. And the other condition is that when one of the bit is complement to the other bit, the in place bit, when one of the bit is complement to the other bit, whatever the carry that is coming from the previous stage will be propagated as it is. If there is no carry, that will be taken as no carry. If there is a carry from the previous stage, that will be taken as carry. So this is 0 1 0 1 sort of thing. That means the same carry will be getting propagated to the next stage if the in place bits are complements to each other. So this is propagate condition. So this is the probable outcome of your complete addition of the in place bits with the carry from the previous stage. So conceptually, if you put this back into the aspect of how you are able to look ahead the value of the carry is that if the in place bits are 0 0, I don't need to wait for the previous bits to generate the carry or no carry. it is not going to get influenced. That is the thing we can assess. If the in place bits are 0, 0, directly you can say that carry is kill. If the in place bits are 1, you can say carry is generated. Whatever may be the conditions of the previous stage's value propagated from, say, you are at stage n and you are plenty number of stages from 0th stage to the nth stage. If you want to travel, I am referring to the ith stage in between, say somewhere in this condition. I minus 1 stages, I don't need to wait that much of propagation time. I'm able to cut down if my in place bits are both 0, 0 or 1, 1. Because obviously the value of the carry will be known for us either as a kill or generate. Okay. The only one condition on which I need to wait, at least for some extent, not that I need to wait right from the first stage till the ith stage, to some extent of one stage ahead. If the in place bits are complements to each other, then what is the stage of the carry, or what is the status of the carry value that is getting generated, or what you say, uh, from the previous stage, i.e. minus 1 stage? That depends, or that decides the value of your carry. So this is something like you're prefixing the value, or you're looking ahead of the value of the carry. So that process will make the iteration to be little bit faster compared to your ripple carry adder, where the carry has to ripple from the previous stage to previous stage, and then ultimately at the ith stage you will be evaluating after I minus 1 clock durations. But here there is no such delay occurring. So something I can put this into this form. Say I'm taking x is some carry condition of I plus 1th stage. I'm taking that with the x of the previous stage. Say the carry of the I plus 1 means that present state, and this is previous stage. That way also you can take. When the carry is, say I'll take this way. Say a kill condition, propagate condition, or generate condition is there in that ith stage. This is based on a of I and b of I if you are taking, and this is a of I minus 1, b of I minus 1 I'm taking. Okay. On this also you take something like this. Both means the same for us now. Carry, kill, propagate, and generate. What is the meaning of this? This is the previous stage, and this is the present stage. If the present bit value of a of I, b of I is either a kill, propagate, or generate, and the previous stage carry condition is either kill, propagate, or generate, what is the present value of the carry? If the present bit is a kill, directly it will be a kill. If the previous is kill or propagate or generate, what is the meaning of the kill? The in place bits are 0, 0. It becomes kill for all previous carry conditions getting cancelled. The previous stage, whether it is the carry, kill, propagate, or generate condition, if the present stage bits are 0, 0, it is a direct kill. If the present bits are propagating, okay, that means 0, 1 or 1, 0 condition is there. Now, the previous stage value is kill. Then obviously this will be kill, because the one that is getting propagated is kill. Kill is getting propagated, and the previous value is propagate, that will be propagated as it is. Okay, and the previous is generate. Now that propagation will be the generated value of the previous stage. Okay. Now the present stage, both the bits are 1 1, irrespective of the previous stage carry, whether it is kill, propagate, or generate. This is direct generate. Hope you are able to understand this now. We are taking the concept of this kill, generate, or propagate for making the iteration faster, making the addition process faster. Hope you understood this. Okay, I'm moving on. Now, in this addition process of something like a prefix adder, some text of a parallel prefix adder, it is nothing but Hawkstone adder. A combination of this along with carry look ahead, if you take, it's a Hawkstone adder. Okay. Another type of adder is Brootkung adder is there. Brootkung adder. KUNG, I suppose. And I think this is not there in your syllabus. If we follow this in left-right order, this will be right-left order. Okay. I don't think this is there in your syllabus. Only up to this we have Hawkstone adder is there. It is a type of parallel prefix adder along with carry look ahead process. So let me first try to give the explanation using a decimal value, then we can go for a binary value. Okay, see, if I have 8-bit value, can take it 1, 5, 6, 7, 8. 8 values are there to be added, each having a positive or negative value, a decimal value we try to take, say positive 15, okay, let me take, say a small number of positive, -1, say 6, positive 1, say 3, 5, 4, say. These are the values in the 8 registers. So for this, +1 register will be taken always in order to have something called as communicating with the neighbor, to facilitate communicating with the neighbor or to talk with the neighbor. Okay, what is the concept of talking with the neighbor is that ultimately the last register should be storing all the uh, results of addition of all the values in each of these 8 registers. Okay, when you are doing the operation of the addition, each register should be talking with the neighboring register or a register at a what you say, a distance of 2 or distance of 4 or distance of 8. Okay, so something like we say that whenever there is an addition of 2 successive registers done, we say that they are talking side by side. The talking happens side by side. Okay, and the second step is, first step is that when I add this, what is the result I will get should be stored in my final register. This register is the final register for us. This is the initial register. When you are adding, so see here, say 0, this is Q0, Q1, 2, 3, 4, 5, 6, 7, and 8 you are having. the concept is that do the addition of Q0 to Q8, and Q8 stores the result of the addition of all 9 values. Okay. So what is the result? Actually, it should be 4 plus 5, 9 plus 3, 12 plus 1, 13 plus 6, 19 minus 1, 18 plus 2, 20 plus 15, 35. So 35 should be there in Q8 after I do the addition operation. Okay. Now for this, the iteration is that when you are adding or when you are doing the operation of adding, first step is every successive neighbor will be talking to each other. Talking means here we are doing the addition process. Every neighboring value will be added. Whether it is a positive value added or negative value added depends on what is the magnitude that is getting stored there. Okay. And it will be storing that value after addition. See, if this stores, this Q8 stores the value of 8, 7 added. Okay, something like this you can visualize. And this Q7 stores Q6 and Q7 added. So 7 and 6. And 6 will be storing 6 and 5 value. This will be storing 5 and 4 value. This will be storing 4, 3 value. This stores 3, 2 value. This will be storing 2, 1 value. This will be storing 1, 0 value. Okay. And this is communicating to the next neighbor. And see here, once you do this iteration, this is 17, this is 1, 2 minus 1, and 6 minus 1 is 5, 6 plus 1 is 7, 4, 8, 9, and this is 4. Okay. Now, and here for this 0 fellow, there is no neighbor. There is no neighbor. So 0 will be 0 as it is. There is no neighbor, so there won't be any value. So we say that this Q0 is settled. Q0 is settled. Next step is, this is a distance of 1 we have taken. The successive neighbor talking is happening, or successive neighbor addition is happening if you are taking it as an adder. Now, the second step is a successive neighbor at a distance of 2, or a neighbor at a distance of 2. Now that means this will be talking with 8, will be talking with now 6. Okay. And this 7 will be talking with 5. And we have this 6 talking with 4. Five talking with 3. 4 talking with 2. And 3 talking with 1. And 2 talking with 0. Now this 1 doesn't have a neighbor which is a -1. 0 minus 1. So this now at this point, this is getting settled. Your Q1 gets settled. Previous step Q0 got settled. Okay. So this is settled with the same value. Now what is that? See here. 8 and 6 talking means this is equal to 22. Is that correct? 22. Next, 7 with 5. 7 with 5. 8. And 5 with 4. 9. Or that 6 with 4 means 5 plus 4. 9. Next, this one. 13 or 12 or 15. 7 plus 8. No one is there. This is 13.
12.
And this fellow is 12. And this fellow is
9.
9 with 9. And this 4 is settled, 0 is settled. Now next is talking with a distance of 4. A neighbor at the distance of 4 we need to take. A neighbor at the distance of 4 means this one. 1, 2, 3, 4. Yes, a neighbor at the distance of 4. It should be talking with a distance of 4. And this fellow, that means 8 will be talking with 4. 7 will be talking with 3. 6 will be talking with 2. And 5 will be talking with 1. Let us see how many neighbors are available for this. 7 talks with 3. So this is 3. 6 talks with 2. 5 talks with 1. And even if you take 4, already settled value you are having, this is 4. Okay. But anyhow, that is getting settled because this is not 0 only. So this gets already settled. So now at this point of time, you have all these 4 settled values. There won't be any change. These are settled values now. Now the values what we have here, see here. 8 and 4 are talking means that 22 plus 13, that is 35. And this is how much? 20. And this is 9 plus 9, 18. And this is 15 plus 4, 19. Okay. Now next, if you have, the next neighbor with which it is talking is to be positioned at 8. But here see, there is no talker which is at a position or distance of 8. You maximum you are getting is 7. No? 1, 2, 3, 4, 5, 6, 7. And this is anyhow the 8th position, or what you say, the talker in this Q0 is already settled. That if you add here, this is 8 with 0. You are getting the final value, and these are not having any further talkers which are positioned at a distance of 8. So these fellows are settled now. All these fellows are settled now. Only the new value or the value which is unaltered when you are having a talker from this one, from this 0. If you take that with this final addition, now this is getting settled. Now that is the value what we are getting after adding all the 8 values here. This is parallel prefix adder concept or else the Coxstone addition approach. The Coxstone addition approach, so this is for decimal values we have taken. We can extend this to the binary elements also. The binary elements also. I hope you understood what is Coxstone or parallel prefix adder. Parallel prefix adder.
Yes, ma'am.
Yeah. Now we can extend this for the binary format. The same element of the talking of the immediate neighbor, that means a distance of 1. Next step, a neighbor at distance of 2, neighbor at a distance of 4, neighbor at a distance of 8. That extends based on how many number of digits you have. So this we try to extend for binary also. Now that becomes the Coxstone binary adder. Okay. For this we can put something like this. Say so here the same logic of our carry look ahead adder element, if you consider, along with the parallel prefix concept, the propagate value is given with an equation of what is the value that will be getting propagated is A and Bi, because A and B are mutually complements, then you get propagate. No? What is that generate? G of I, A of I, B of I. What is kill? Kill we are not taking because that kill is what is a complement of the values. Like we are not taking that values. P of I complement. Can I take this way? Is this correct? Kill condition.
Yes,
But kill
ma'am.
condition we are not taking here. We are interested in generate and propagate alone. Okay. And this propagation, or what you say, the generation along with propagation complete we take, we define these stages of addition that we took 4 stages of talking, no? 4 stages of adding. So something like this generate, the present state generate value will be taken from the present propagate and the previous stage generate star or whatever we indicate as the previous stage or the generate of the present stage. Anything it is resembling your previous equations, previous adders equations. When you take this as a carry look ahead concept, what is that getting generated is the previous stage generated value. Na? I think I have given you the table. In the table, we have defined this. Na? What is that getting uh, generated or propagated? In the present stage, okay, what is that getting generated? Present stage, the generation, whether it is the previous kill, propagate or carry, it is a generate when it is equal to 1. That means both inputs are 1. But the propagate condition, if you consider, what it will be propagated is the previous propagate value, or what is that propagated will be the previous generated. See here, this one. What is that getting propagated is the previous stage G generated value. The present propagate is the previous generate. and or what you can put is you can get the generated value when the in place bits are both 1. So this is the condition what we are getting in. So ultimately in total, if you take the present generate value is equal to the propagation of the previous stage and the generation of the present stage, both mixed together. That is the equation what we are getting here. This one. And what is the propagate value of the present thing? P of I. P of I of the star means the previous stage propagated value. Okay. Now try to take an example or a value and do this now. Say if your A and B are both something like, try to take this one, take these two equations as it is here, and the sum and carry, if you can evaluate what is S of I. This is P of I, Ci minus 1, and C of Ig is generated, if I'm correct. All these equations are similar. Now, to which context you are taking in, to that we'll be evaluating based on that equation. Okay. Okay. Let us take 1 0 1 1 and 0 1 0 1. What should be the result for us now when you are adding these two? 1 0 1 0 0 1 0 1.
Not 0 0 0.
Okay. Now the stages, if you are considering 4 stages, what is P and what is G? What is P and what is G? Those two values we need to take here. For independent, each stage propagate and generate, propagate and generate, propagate and generate. Here, generate is 1. First stage, this stage. Generate is 1. Propagate is
1. 1.
no. Generate is 1. Propagate is
0.
Is there any carry from the previous stage? No, no. First thing, we are not having any carry from the previous stage, no?
Yes, ma'am.
If generate is 1, propagate is 0, no?
Yes, ma'am.
Next here, 1 0. Generate is 0. Propagate is 1. Generate is 0. Propagate is 1. Generate is 0. Propagate is 1. Okay. Now from this, we need to have the nearest neighbor talking at the first stage. The nearest neighbor is talking. Now tell me what is the generate and propagate. Now you have to take these equations. These equations you need to take. Carry is 0. Carry is 0 here. What are the values you'll be getting? Generate is 1. Previous stage carry is 0. C naught is 0 if you take. Now propagate is 0. Here. Hmm. Generate 1. Propagate is 0. Here. Generate is 0. Propagate is 1. Wait. Previous? Here. No. Propagate is
0 or 0, ma'am. So 0, no, ma'am.
1 and 0, na? These two propagates, na? 1 and 0, na? 0. 1 and 0. 0, na? One.
Ma'am, generate bit, not propagate.
Generate bit either propagate or the previous thing or the generate one. Na? You are getting 1, na? 1 and 1 or this is 0. So it is 1. P G I minus 1. P G I minus 1 is 1, na? And present G of I is 0. But one of the condition is 1. So you are getting 1. Understood? This is present P of I. And this is Gi star. Na? This is Gi star. Previous will be Gi star. So these two, if you group together, that is 1 only. Na? 1 or 0. 1 or 0. Here, why we are getting 0? This is 1 and of 0 is 0 or 0 is 0. Propagate of this stage and the previous stage is 1, this equation, so it is 1. I'm taking these two equations, and this is 0, 1. Now communicating the neighbor that is at distance of 2 is this stage. So here this C naught will be 0 now. So here we can take that this is settled. This is settled, though you can have this as 0. This is settled. And this is also settled. So this is 0, 1. Okay. Now see here, what is the value you are getting? This is, see here, this is present P, this one is 0, 1, and this one is 0, 1. So take the value of sum and carry as the P and G concept. Okay, so sum will be 0, carry will be 1, sum 0, carry will be 1, sum 0, we are getting. So ultimately, what is the result? This is sum 0, this is 0, this is 0, this is also 0. And what is the carry you are getting here? This is 1. The carry is 1. So this is the result.
Ma'am, so from last bit only, we should take the carry.
Yes, yes. Final, no? This is the final one. This is your carry, final carry.
So previous carries are all neglected.
No, that is going off when in the process of adding to the next higher level. No, these are all already used carries. For generating this, already these carries are used for us. That is the meaning, no? When you are communicating with the next neighbor, this carry is getting used. When you are taking the neighbor placed at second position, means you are taking the carry from the earlier stages, previous stages also. Carries of 2 stages considered here, carry of 4 stages will be considered here. This is 2-stage carry complete, 4-stage carry complete. So all the stage carries will be reflecting at the final carry, because this is the position, or this is the uh, place where we will find the final result or final bit. If it is decimal, final result, total complete result. If it is binary, the sum and carry of the last bit will be taken from this here. Sum will be automatically the concept of P of I and Ci minus 1 coming. Carry will be the final G of I, final G of this one, final G of. If you have still any doubt, you can take one more example and see it. 0, 1, 1, 0. Let us take, and what is the other one we can have is, see, all ones you take. What is the result you will get? You see, all ones. No, let us take 0, 0. That means 0, 0, 1, 1, 0, 1. Try to check for this and give the result. There should be this result. And do for this also. 1, 1, 0. 1, 1, 1, 1 if you are taking 1, 1, 0. 1, 1, 0, 1. Try to work it out. If you want to do it as assignment, you take it as assignment. You want to work it out now, you can work it. I'll give you 2 minutes time. Say for this example, if you take just the first step I'm giving, the next steps you try for yourself. What will be the propagate, generate, propagate, generate, propagate, generate, and propagate, generate? For these 2 bits I'm taking. Propagate, generate is 1, 0, 0, 1, 0, 1. And this is 1, 0. For second thing I'm taking. Second value, not first one. Mm. No, first set what we take is this format. No? First deciding parameter. AIBI, XOR of AIBI. Generate is AND operation, and propagate is XOR operation. That way I have taken. That is first guiding equation for us. And this is settling now. Already settled 1, 0. Next, I hope this should be 0, 1. If I'm not wrong. And this is, I think this is 0. Is this 0?
Zero one, ma'am. Second one.
That is also 0, 1. Huh?
Yes, ma'am. Only last one is 1 0.
0. This one is 1, 0, and this is 0, 1.
That's
Is that correct? So this you are getting it as 1, and this is 0, 1. Huh? Now what is the sum and carry? I think this is the sum and carry. This is settled. Check it out. 1 0 1 0 1 we need to get. 1 0. That means your carry should be here 1, sum should be 0 here, and sum should be 1, sum should be 0, and sum should be 1. Check it out, like from the first stage you check it out whether you are getting that as correct or not. Do this as assignment evaluation for these two examples. Foxstone adder for binary. Parallel prefix, one more question I gave. 12 minus 3, 4 minus 2 plus 5. 1, 2, 3, 4, 5, 6, 7, 8. Okay. For this, you do the parallel prefix addition, get the result. That is one more assignment question. Okay, I'll stop here today.
Ma'am, I have a question.
Yeah. Your voice was breaking, Meghna. Repeat.
Ma'am, no, I have a question.
Yeah, tell.
How do we determine the carry bits in this Cogstone adder? I don't understand that. Carry bits.
Yeah, we have these equations. No? These are the guiding equations. The carry bit actually for our addition process is after the final step only we need the carry bit. Yes or no? In between carry we don't want because that is not going to give us the result. So in between carries we won't bother. We just define or we just concentrate on what is the carry status, whether that is getting killed propagated or generated will be evaluated based on the in-place bits. That means these bits. These bits with these parental bits, these are our main bits. No? With this, we try to define whether the carry is getting generated from this stage or propagated or killed. That means K, P, G is the concept we are trying to evaluate. When we are doing this KPG analysis, until this final stage, we don't need to memorize that or consider that for the final result. Only the last one, last carry only is the one which is of our interest. So what we do is, first we try to like finalize the bit values until we get the final the neighbor. We go on doing the iteration of what is the carry, generate and propagate concept. We try to generate that. I think this is the one what is going to give us the answer. Using this concept, this table, we are generating or propagating the carry from every stage. This is each stage. No? So finally, once that register or that bit position is getting stabilized, so this is the stage where it is getting stabilized. There is no further neighbor available, means that it is stable. At that duration, we try to take what is the value of generate is equal to the carry. Okay, what is the value of generate we get is the carry. And what is the sum we try to evaluate is that pth stage, that means ith stage propagate with the previous stage carry. Ith stage propagate with the previous stage carry. Okay, that gives the total. Like after each register gets stabilized, after each stage is getting stabilized, then we try to evaluate what is the value of that ultimate result of the sum and carry. For this sum and carry value will be evaluated once all the stages are getting stabilized. What is the meaning of stability is until there is no neighbor, or until we get the final neighbor of every stage, we will be going on evaluating the propagate and generate. Once the neighbors get seized, there is no further neighbor available, then we say that that stage is stabilized. So that is the way we are trying to evaluate. So every stage we don't need to evaluate the carry. Only the thing what we need is the final stage carry, and the each stage sum is needed.
Okay, ma'am. Thank you.
Okay, today I'll stop here. If no further queries, we can stop this class.
Thank you, ma'am.